Chapter 1 Rational Numbers Part 2. By the end of this session, you will be able to enlist properties of rational numbers, identify additive inverse, explain reciprocal of a number, define distributive property. We define a rational number as a number that can be expressed in the form P upon Q, where P and Q can be any integers, but the denominator Q cannot be equal to 0, as anything divided by 0 cannot be defined. Now we are going to see the properties of rational numbers. Under properties, we are going to study closure property, commutativity, associativity, the role of number 0, the role of number 1, negative of a number, reciprocal, distributivity of multiplication over addition. Now let us study closure property in detail. Definition. A set is closed under a mathematical operation if performance of that operation on members of the set always produces a member of that set. Which means that if you are doing any mathematical operation on two set of numbers, then the result should be the same set of numbers. To understand this better, let us consider the set of natural numbers. Here you can see that while adding two natural numbers, we always get a natural number. Hence, it is closed under addition. Here we see that while subtracting, we may or may not get natural numbers as result. Hence, it is not closed under subtraction. For multiplication also, we can see here that when two natural numbers are multiplied, we always get the answer as a natural number. Hence, it is closed under multiplication. In the division, we see that sometimes we might get natural number as answer, or we might not get natural number as answer. Hence, it is not closed under division. Now, let us extend our understanding for other set of numbers. Let us recall closure property on the set of numbers studied in previous classes. In the previous slide, we have seen that for natural numbers, closure property holds true for addition and multiplication. That means natural numbers are closed under addition and multiplication. Natural numbers are not closed under subtraction and division. Now let us see whole numbers. Under whole numbers also, we can see examples where we conclude that whole numbers are closed under addition and multiplication, whereas it is not closed under subtraction and division. Similarly, when we apply closure property on integers, we see here that for addition it is closed, for subtraction also it is closed, multiplication also it is closed, but for division it is not closed. Now Let us apply our understanding of closure property on rational numbers. Now let us see the operation addition. Here, based on the example, we see that whenever we add two rational numbers, we always get the result as rational number. Hence, we say that rational numbers are closed under addition. Now consider operation subtraction. Here also we see that when two rational numbers are subtracted, we always get the result as a rational number. Hence, we can also say that rational numbers are closed under subtraction. Now consider multiplication. Here also we see that when any two rational numbers are multiplied, we always get the result as a rational number. Hence, rational numbers are also closed under multiplication. Now consider division. Here we see that when any rational number is divided by 0, then we cannot get a rational number because we know that any number cannot be divided by 0. It is not defined. Hence, for rational numbers, it is not closed under division. Now, let us understand the next property, commutativity. Commutativity states that when two or more numbers are mathematically operated, the result remains same irrespective of the order of the number. To understand this better, let us consider the following example. Here, 5 plus 3 is equal to 8, so is 3 plus 5. Here we can see that the order of the number does not change the final answer. Let us see another example. 2 multiplied by 3 multiplied by 4 is equal to 24, and 4 multiplied by 2 multiplied by 3 is also 24. Now let us explore commutativity on natural numbers under the 4 operations. Now see addition. Here 2 plus 5 is equal to 7 and 5 plus 2 is also equal to 7. Since both are equal, we say that addition is commutative for natural numbers. Now see subtraction. 8 minus 11 is negative 3, whereas 11 minus 8 is equal to 3. The answers are not matching. Hence, we say that it is not commutative. For multiplication, we change the order and we see that the answer remains same. So we say that natural numbers are commutative for multiplication. When we divide two numbers, we see that the answers are not coming equal if we change the order. Hence, we see that it is not commutative for division. Similarly, we conclude that for whole numbers, addition and multiplication are commutative, whereas subtraction and division are not commutative. Also, for integers, addition and multiplication are commutative, whereas subtraction and division are not commutative. Now, let us apply the understanding of commutativity on rational numbers. Under addition, we have taken an example 5 upon 7 plus minus 2 upon 3 equals 1 upon 21, and when we change the order of the rational numbers, we also get the answer as 1 upon 21. Hence, the answers are equal. So, we say that it is commutative under addition. For subtraction, 5 upon 4 minus 2 upon 3 is equal to 7 upon 12. Whereas when we change the order of the rational numbers, we get the answer as minus 7 upon 12. The answers are not equal, not matching, hence they are not commutative. For multiplication, we multiply 3 upon 7 into 3, we get the answer as 9 upon 7. And we observe that when we change the order of the rational number, we still get the same answer. Hence, it is commutative. For division, when we divide minus 5 upon 4 by 3 upon 7, we get the answer as minus 35 upon 12. And when we change the order, we see that the answer is 12 upon minus 35. The answer is not matching, hence it is not commutative. Now let us explore the next property, associativity. Associativity states that when three or more numbers are mathematically operated, the result remains same regardless of how the numbers are grouped. Consider the example. We are multiplying 2 into 3 into 5. Here we are first grouping 3 into 5 to get 15, which is then multiplied to 2 to get 30. The same numbers are again multiplied, but here we are first grouping 2 into 3 to get 6, which is then multiplied with 5 to get 30 again. We observe that in both the cases we are getting same answer. Now you explore the next example for better understanding of associativity. Hence, based on our understanding of associativity, we conclude that for all the set of numbers, that is natural numbers, whole numbers, integers and rational numbers, addition and multiplication are associative, while subtraction and division are not associative. The role of 0. Let us explore and observe the following examples carefully. 6 plus 0 is equal to 6. Minus 2 upon 3 plus 0 is equal to minus 2 upon 3. 0 plus minus 8 is equal to minus 8. Here we observe that when 0 is added to any number, we get the result as the same number. Hence, we can say that 0 is the additive identity for all set of numbers. The role of 1. Now let us explore the following example carefully. 5 into 1 is equal to 5. Minus 2 upon 7 into 1 is equal to minus 2 upon 7. 1 into minus 7 is equal to minus 7. Here we observe that when 1 is multiplied to any number, the result is the same number. Hence, 1 is called the multiplicative identity. Negative of a number. Consider the following example carefully. Minus 2 plus 2 is equal to 0. The addition of these two numbers results in additive identity. Here 2 is the negative or additive inverse of minus 2. See the next example. 2 upon 3 plus minus 2 upon 3 is equal to 0. Hence, minus 2 upon 3 is the negative or additive inverse of 2 upon 3. In general, for any rational numbers, a upon b, if a upon b plus minus a upon b is equal to 0, then minus a upon b is the additive inverse of a upon b. Please note, always convert the rational numbers into standard form to calculate its additive inverse. Reciprocal. See the following example. 3 multiplied by 1 upon 3 is equal to 1. When we are multiplying 3 with 1 by 3, we are getting the result as multiplicative identity. Hence, 1 by 3 is the reciprocal or multiplicative inverse of 3. Similarly, in the next example, we have 7 upon minus 5 multiplied by minus 5 upon 7 is equal to 1. Therefore, minus 5 upon 7 is the reciprocal or multiplicative inverse of 7 upon minus 5. In general, for a rational number a upon b, c upon d is the reciprocal or multiplicative inverse if a upon b into c upon d is equal to 1. Please note, 0 has no reciprocal because we cannot divide any number with 0 as it is not defined. Distributive property. For any rational numbers a, b and c, the following formula is distributivity of multiplication over addition and distributivity of multiplication over subtraction. To understand these formulae, let us go to the next slide. Let us understand distributivity of multiplication over addition. To understand this, we have taken three rational numbers minus 3 upon 4 as A, 2 upon 3 as B and minus 5 upon 6 as C. Now in the LHS we are taking the expression A multiplied by B plus C in the bracket and we solve as per the expression. After solving, we get the final answer as 1 upon 8. Now consider RHS. RHS, we have taken the expression A multiplied by B plus A multiplied by C. By solving using this expression, we are also getting the answer as 1 by 8. Hence, we have LHS is equal to RHS. Hence, the property distributivity of multiplication over addition holds true. Similarly, the property distributivity of multiplication over subtraction also holds true.